And welcome everybody to the start of chapter 7. So now we're going to get into a little bit more challenging problems. We're going to start adding not only series connections but parallel connections in the same circuit. And so the next couple of chapters are going to deal with a lot of different variations of a series parallel circuit. But this one, we're just going to show you how to do the basic calculations for a series parallel circuit and what that means and how to obtain RT and then find the current, and then we'll be utilizing voltage division and current division. So that's why it's so important to learn it in the previous chapters. So let's go ahead and get started. Just to refresh, a series circuit, a purely series circuit, has one continuous path through its components. When it's connected to a supply, excuse me, the current flowing into a component must equal the current flowing out of that component. So an essentially series circuit is what we do with series parallel. What we do is we reduce the parallel combinations and the series and parallel combinations all throughout the circuit until we get down to what we call an essentially series circuit. It says, if all branching currents are zero and what remains is a circuit with essentially the same current, the circuit is considered to be an essentially series. So when I do my analysis, I'm going to get to the point where I say, okay, now we're at an essentially series circuit, and that part of the analysis we will treat as if it were just a couple resistor series circuit or whatever. Okay. Now, just to review parallel circuits. Parallel circuits, the above figure demonstrates a parallel circuit. All three of these components are in parallel with each other, and what do we know about parallel circuits is that they all have the same voltage drop, so V1 equals V2 equals V3. However, they will draw different currents, okay? Or whatever current is coming into this node, it's going to be split up depending on their value. And so the lowest value resistor should get the highest percentage of the current, and the highest value resistor should get the lowest percentage of the current, because it's going to be splitting it up. Whatever comes into this node, KCL tells us it has to leave. So in this case, we would have a total current that comes into this node here. It gets split three ways and then combines back together on the other side. But they would all have the same voltage drop. So different currents, same voltage. Okay? It says when connected to a voltage supply, that's basically what I just said here. The voltage across each branch must be the same. Okay? Now, we are going to start combining those two things together, right? So the easiest, most straightforward version of this is what you see in letter A, where you have, presuming that there's a source over here that's part of this network. But anyway, if you were to come out of the source and into this 1 ohm, or this resistor 1, component 1, and then that's going to go through that component and into this node right here, and then it's going to split between 2 and 3. Okay, so there's going to be a total current, which is what is going to flow through the component 1, and then there's going to be two more currents that split off from that and then combine back together. So we have to figure out, same principles. We are looking at current division, we're looking at voltage division, we're looking at Ohm's law. Ohm's law is going to play a big part of this as well. So what we're doing is we're trying to get each one of these down into what we called, in a few slides ago, the essentially series circuit. Okay, and so here's how we do that. We have to look at the totality of the circuit before we try to do anything individually. Okay, so in this circuit here, all right, we've got definitely got some resistance, some series and parallel resistance going on here, okay? So essentially what we're going to do is we're going to start farthest away from the source and try to reduce this network down to an essentially series circuit. So this slide is calling these things sub-circuits. You don't really have to look at them as that, but really that's how they operate, okay? So what I see here, if I just look at these three branches, I realize there's something going on over here in this branch, but these three branches I notice are in parallel with each other. Okay, that's what you see in the purple. These two resistors out front here are both in series with the source. Do you see that? Out of the source, there's no breaks, there's no nodes. It's just one single continuous path until it gets to this node up here. Okay? So these two are in series with each other. This branch, and this branch are in parallel with each other. So when we do our analysis, these two resistors will be added together, and equivalent will be put in its place. And then these three branches will be taken in parallel, and a single equivalent resistance will be put in their place. Now, over here on this parallel branch that we've got here with R3 and R4, you see that there are two resistors in series. There are no breaks. So on this branch over here, we can look at these two together as if they were a single resistance. And then once we find that single resistance, we can take these three in parallel, find that equivalent resistance, and then take that equivalent, essentially what all of the purple reduces down to, a single resistance. That resistance plus R2 plus R1 will give us our total resistance for the circuit. So that's the very first thing that I do when I do a series parallel circuit. And you always hear me say Chapter 7 methods. Well, here's the first part of the method, is to find the total resistance. Okay? So what that means is we need to start reducing the series parallel resistors. All right, so let's look at an example. This was letter A in the previous slide. So here we've got 2 and 3 are in parallel with each other. Once we find that equivalent resistance, we could rewrite the circuit and say that this is 1, and that is now in series with what we just calculated. Okay, this parallel, here it's showing it as a double forward slash. The way that's typically shown is by two straight poles. So instead of, I can't edit that because it's a picture, but instead of having the forward slashes or back slashes, they're just straight up and down. So 2 in parallel with 3. You'll see me write that on the board. Okay. Now, once we have this situation here, we have an essentially series circuit. So I essentially just need to add all of the rest of them together since I have a series circuit at this point. And so now you can see the total resistance here is 1, whatever this is, plus the resistor 2 in parallel with 3. So this calculation has to happen first to get it to replace it down to a single resistor, and then you can add everything together. Okay? Now, I like what it says here because typically you start on the right side of a schematic. When I'm talking about that, if I come back to here for reference, here's the source, and almost always when I do a circuit, unless it has multiple sources, if I do a single source circuit, I always put it on the left. And so that means that we want to start furthest away from the source and work our way back. So when you see here that it says typically start on the right side, that's why it's in quotes, because depending on how you draw your circuit, it could be on the left side that you start. So really, I think the ultimate point that's trying to be made in number 1 here is that you want to start as far away from the source as possible, okay, and work your way back. So combine any parallel resistors that both meet at the ends to a single resistor, redraw the circuit, and then once you have a series circuit, add them all together. Okay. So here we go. Here's another series parallel combination, and we assume that the source is over here on the left. So what we do is we start furthest away. Okay. So the furthest away right now, I'm only going to look at this branch out here and this one because this one is in parallel with this. Okay. Now, to do that, before I do that, I have to combine these to a single resistance, okay? So these two are in series with each other on this branch out here. So first thing I do is I draw a single resistor for those two. And there we go, okay? I essentially just replace that entire branch with an equivalent series resistance. All right, now I've got this branch in parallel with this one right here, and so now I take those in parallel with each other and redraw it, okay? Now, when I say redraw it, it's between this point right here and right here. That's what gets replaced. So, you know, it's not drawn over here, but I would have a little dot here and a little dot here to signify that these two reduce down to a single. Okay? So, now that I have an essentially series circuit, you can see down here I can just add 1 to whatever this thing calculates out to be. Okay? But again, I'm going to have to take the series circuit first to find the total resistance on this branch, take that branch in parallel with this one to get an equivalent resistance there, and then I can add them all together. We're going to follow that over and over and over, and it doesn't matter how complicated or how simple this series parallel circuit is. Okay. A specific type is called the ladder circuit, and I'm going to be doing a few of those. And it has this generic format where you've got one resistor here, and it has this network, and sometimes there's more than just 4 of these out here, okay? And it says to analyze a resistive ladder circuit, the circuit must first be reduced to find its equivalent total resistance, and then you can calculate everything else. So if we were going to reduce this ladder network down, okay, we have a nice little diagram to show that. So we're assuming 3 and 6 are the 2 values that we're using. So they did this to make it easy so you can just do the calculation in your head. So on this outer branch here, or again, we're starting farthest away from the source. So we want to start out here with these 2 branches. We don't care about anything else back here, only between this branch and this branch. That's it, because that's what we're going to replace. So 3 plus 3 is 6. So if we were to rewrite this with an equivalent 6 ohms resistance here, now I take this branch in parallel with this branch. Well, anything in parallel with itself, you divide it by 2, right? So 6 in parallel with 6 is 3. Okay, so right there, these 2 got reduced down to a single resistor, right? As if there were just a 3 ohm resistor here. So now over here, I've got 3 plus 3 again. So before I do these 2 in parallel combination, I have to add those 2 together. So now I have a 6. These 2 will be taken in parallel. 6 in parallel with 6, divided by 2, and you get a 3 equivalent. All right, so now I'm down to an essentially series circuit, right? So I've worked these 2 down to, or I worked these 2 to a single, these 2 branches to a single one, and then these 2 branches to a single. So now I have 6 total ohms of resistance in this circuit. So you might not be able to notice that or be able to tell if you just look at the circuit up here. Now I know that this is an R2R ladder, and so I would have known that there's 6 ohms if I knew what R was and what R2 was, or 2R. But I will do a few of those examples as well. And I think this is probably a good time to get off the PowerPoint and go straight to the board. Okay, so I'm trying to stay out of the shot there. So the very first circuit that I'm going to look at here is the simplest one that we can make with just 3 resistors, okay? And these are in your parts kit, a 1K ohm resistor, 2.2K, and a 3.3K. And I'm going to simulate the 9-volt battery. And then we can also look at how you would set that up, because it's a little bit different than just a straight parallel or series circuit, okay? So the first thing I want to do is between here and here, okay, I want to find the total resistance, okay? So the way that I do that is I essentially remove the source, and I draw my circuit, 1K, 2.2K, 3.3K. And as I go, I'm going to step this out and say, okay, what changes from this circuit to this circuit? And then I'm going to redraw it. And then what changes from that one to this one, so that I can go back and recall these calculations, because everything you do here, you're going to want to come back and look at later. So the very first thing I need to do is I need to take 2.2K in parallel with 3.3K. And to remember how to do that, go back to the parallel combination lecture, chapter 6. So I've got 1 divided by 2.2 plus 1 divided by 3.3. Take the whole thing to the -1, and I get 1.32. So REQ for those 2 is 1.32 kilo ohms. Okay, so now I can rewrite this. This is why I say it's the easiest one, because you only have to do 1 parallel combination. So 1.32K, and this is my 1K. So what I did here is from this point to this point, if you can see that in the red, okay, that's this and this. So essentially, I came up with what the equivalent was. If you were to take an ohm meter and put these two in parallel and measure it, you will get around 1.3 kilo ohms. Okay? So now that I have these together, I have an essentially series circuit, and I can find my RT is 1K plus 1.32K, which is 2.32K. So let me go ahead and write that up here. So RT is 2.32K. Now I want to remember that these two in parallel, so 2.2K in parallel with 3.3K, because I'm going to use this for my current division later. So I want to remember that that one was 1.32. Okay? I don't have a lot of space here, so that's why I'm writing everything up top. Okay. All right, now that I have that information, I can go ahead and find the total current, which is, nothing has changed. It's still Ohm's law, right? VT over RT. I'm just rearranging Ohm's law. So the current is going to be the total voltage divided by the total resistance, which we found is 2.32K. So 9 divided by 2.32. I get 3.88 milliamps. That's the total current. So that's what's coming out of the source and into this top node up here. So that is 3.88 milliamps, okay? And so now what's going to happen is that's going to come into this node and split. And it's going to split this branch and this branch. And this is why we want to remember what we had for these two in parallel, because now I have a current division problem, okay? So if I wanted to find the branch current for the 2.2K, all right? Remember with current division, it's whatever comes into the node, which is 3.88 milliamps times, okay? This time it's the total over the individual, so 1.32K over 2.2K. So just to remind you where we're at, had a little technical glitch. So got a current that's coming into the node, and then two currents that branch off from that. Okay, so out of the source into this first node, that will split up here and here. So the total current, I can now find what the total voltage divided by the total resistance. And this is 9 volts divided by 2.32K, which is 3.88 milliamps, which I may have already done the calculation for. I'll have to check the video later. If I want to do the individual branches, right, so we've got 3.88 coming into that node, okay, and it's going to split. Part of it's going to come this way, part of it's going to come this way. So if I want to find the current through the 2.2K, this time I'm going to use current division. Okay, I've got 3.88 milliamps coming into the node. And remember, for current division, you have to use the total on top divided by the individual. So for this one, it's 1.32K. And again, that's why we kept this number up here over 2.2K. And the calculation I found was 2.33 milliamps. Okay, so that's what we found here. So 2.33 milliamps comes this way, assuming we did the math right. And then of the 3.3K, I expect this one to be smaller because this one is taking up almost all of the 3.88 milliamps because it's smaller, right? So less resistance, more current. So 3.88 milliamps times 1.32K, again, that's those two in parallel, divided by 3.3K. And this time I got 1.55 milliamps. Okay. So these two numbers do add up to 3.88, so I think I'm correct. So 1.55 milliamps, okay? Now that you have all of the currents, you can find all the voltages and you can find all of the powers, okay? So I'm going to get rid of this here because we have everything we need now. And we'll just choose one of the resistors, okay? If you know the current through a resistor and you know the resistance value, then you can find the voltage drop. So how about the voltage of the 3.3K? Well, I've got a 1.55 milliamp current, and it's 3.3K. So this voltage drop is going to be 5.12 volts. And the voltage of the 2.2K is 1.55, I'm sorry, yeah, it's not 1 point anything, is it? It's 2.33 milliamps times 2.2K. Now, I predict that these two are going to be identical, and I hope that's the case because this branch is in parallel with this one. So these two should have the same identical voltage drop. So 2.33 times 2.2, and I get 5.13. So they are the same. Okay? So that leaves me with what? Just under 4 volts for this one. But we know that because it's a 1K, right? So 1 times 3.88 is 3.88. Kiloohms times milliamps is just volts because the kilo and the milli will cancel. But I'm going to write it out anyway. Voltage of the 1K. So we've got 3.88 milliamps times 1K. Again, the K and the milli will cancel, and you get 3.88 volts. Okay? And then if you wanted to find the power, you could just take the voltage drop of each one, the current of each one, and then do your calculation. Okay? Okay, now we're going to take a look at Multisim and see if what I did is correct or not. Okay, so I'm going to go ahead and come over here and grab a meter. I've already plugged the circuit in, so you don't have to watch me do that. And this is just going to read the voltage, just to see if I'm on the right path. Okay, so I've simulated it. There we go, 3.88 volts, which is what I calculated. All right, now let me go ahead and throw a couple of ammeters in here, or these current probes. There's the 3.88 going into the node. Here is 1.55 on this branch right here, and then finally there's my 2.33 milliamps. So this is the method that I would use to tackle all the Chapter 7 problems, is to do them on paper, make sure that you understand what's going on, and then come in and let Multisim tell you if you are correct or not. Okay? All right. Let's get back. All right, and the next example that I'm going to do here, a little bit more complicated now, if I can find my markers. So this time we've got multiple branches going on here, and we've got multiple different resistor values, and they're all different so that I can always refer back to them. And so the first thing I'm going to do, again, I know I have a 9-volt source here, but if I were to take this 9-volt source out, and if I were to put an ohm meter in its place, essentially that's what we're doing here, right? We want to find out what the total resistance is. And when I do this in Multisim later, I will show you how you can calculate that, or how you can measure that without a source in, okay? So we want to start farthest away, and we're just going to look at these two branches. We don't care about anything else back here. All we care about is what's happening between here and here. Okay? So I can see that this 1.2K and this 3.3K are in series with each other on this branch, and that this branch over here is in parallel with that one. So, essentially, from here to the next circuit that I'm going to draw, I'm going to add these two together, right? So 1.2K plus 3.3K is 5 I'm sorry, 4.5K. Okay, and that's going to be in parallel with this 5.6. So I'm taking 4.5K on this branch in parallel with the 5.6K on this branch. So let me go ahead and pop that into my calculator here. So I go 1 divided by 4.5 plus 1 divided by 5.6. Take the whole thing to the -1. Whoops, forgot to. Helps if you have the parentheses in the right spot. 2.50. So REQ equals 2.50K. All right, I'm going to go ahead and redraw this. And I'm crunched for space here. So this is not as small as I normally write for this. Okay, so now I'm taking those two and I have an equivalent. So remember, it's like I'm taking all that out from that point to that point and plugging a single resistor in its place. And that's this 2.50K ohm resistor. Okay, so what am I doing now in this next step? Okay, now I'll mark it with blue. Whoops, not with that blue, I'm not. How about green? Okay, so now all we care about is this branch right here and this one over here. And obviously I see that these two are in series with each other now. So I'm going to add those together first. So 4.7K plus 2.5K. That gives us what? 7.2K. All right, so I'm taking 7.2K in parallel with 1K. All right, so let me do that on my calculator. 1 divided by 7.2 plus 1 divided by 1. Take the whole thing to the -1, and I get 878 ohms. So REQ equals 878 ohms. Okay, well, now I'm going to go ahead and replace that. And again, that's my two greens right there. I take all of that out and replace it with that equivalent resistor. Okay. Now you can see this is what I was discussing earlier, that you have to get down to an essentially series circuit. And that's where we're at right here. Okay. So now I can go ahead and say the total resistance is 2.2K plus 878 ohms plus 500 ohms. So 2200 plus 878 plus 500, and I get 3.58. Kilo ohms. Okay, so now that I have the total resistance, the next step is to find the total current. And so now this time I remember I have 9 volts divided by this 3.58K ohm. I'm going to write that off to the side here. So total resistance was 3.58 kilo ohms. Okay. And I'm going to do the calculation here. So 9 divided by 3.58, 2.51. milliamps. So now I know what the total current is. So out of the source, I've got 2.51 milliamps. Okay, now we know what happens, right? It breaks up here. This portion up here breaks out here, and then what happens when it comes back, right? These two come back together so this current down here equals this current up here, right? And then these two come back together for the total. So through the 500, I know what that current is as well, because all of this is in series with the source, okay? If you wanted to, you could look at this as its own branch out here, okay? All of this stuff, until you get to a junction, until you get to a place where it breaks into more than 3 components meet at the same time, these are all in series with the source. And so they are all 2.51 milliamps. Okay? Now, I left all my work up here because I want to start with this one. I don't want to come back to this part yet. I want to use this one that I redrew earlier. Okay, so now that I have the total written down, now that I have the total resistance written down over here, just for reference, I'm going to go ahead and erase this part. And then just look at this, because I can still, you know, if the green represents my total current, I already know what those two are because those are the 2.51. Okay, I want to know how that 2.51 splits up here and here. Okay, so I'm going to use current division to find out what these two are. So the first one, I1, will be this 1K, so I sub 1K. So we know there's 2.51 that comes into the node, right? Times, this is why we kept this calculation over here, because these two branches over here are in parallel, and their parallel combination is 878 ohms. So that's the total resistance of these two branches, the way that we have it written. So that's going to be 878 over, this time it's 1K. Now, this one is a lot less than what's over here, and so I expect this to take the majority of that 2.51 milliamps. So times 878 divided by 1,000, and I get, well, how about we type it in right? 2.51 times 878 divided by 1,000, and I get 2.20. So it's taking almost all of it, all right? So that is 2.20 milliamps, okay? So the rest of it, the roughly 0.31 milliamps, I'm still going to do the current division to verify that. But now I want the current of the, I guess you could say it's the 4.7K plus 2.5K, right? If you want to get specific about it. This is the current for the 1K. This is the current for this branch over here. Okay. 2.51 milliamps. The only thing that's different here, we have the same total resistance for both branches. Only now instead of 1K, we have, what was this? 7.2K. Now I'm going to report this. This is going to, you know, there's 0.31 milliamps left over, but I want to report this in engineering notation. So now instead of 1,000, it's 7,200. And I get 306 microamps. Okay, again, if you have your calculator set up properly, you do not need to do that conversion. It will automatically spit out 10 to the negative 6 there. Okay, so now I know this 306 microamps. So now how do I transfer this stuff up here? Well, the 1K is just its own thing right here. So you can redraw here. This is 2.2 milliamps, okay? Now this 2.5K is made up of other resistors. So the 4.7 is the same. So we know that the current through the 4.7 is 306 microamps. So that's what comes into this final node up here at the top, okay? So now I'm going to go ahead and erase this so I have some room. So now I'm going to figure out how it splits up with these two. Okay. All right, so up at the top here, I'm running out of colors. I don't think the orange doesn't show up well enough. I'll just do it in black. That's okay. All right, so for these last two, all right, the first current I'm going to look at is the 1.2K plus the 3.3K. Okay, and all I'm doing here is I'm just referencing which branch I'm talking about because I didn't label my branches. I don't have that much room up here. So I know what comes into this node is 306 microamps times, again, this parallel combination between these two right here, we found that as 2.5K, so that's the total, 2.5K, all right? The individual over here is going to be 4.5. Okay? So let's see what it is on that branch. 306 times 2.5 divided by 4.5. I get 170 microamps. Okay? Now, this one is smaller than this one, so I expect this next current to be smaller. Okay? So the current now of the 5.6K is 306 microamps times 2.5K divided by, now this time is 5.6. Find that new calculation. And I get 136 microamps. And so that adds up to 206. So I think we're good here. All right, so this one is 170 micro. I know this is tough to see. And this one is 136. I'll work on getting some more colors. 136 micro. Okay. Now that we have all of the currents, I'm going to get rid of all this stuff up here because we no longer need it. And now I just use Ohm's law for everything. And Watt's law, if I want to find the power. I no longer need this either. Okay. There we go. So I'll just pick a couple of random ones. How about the... Well, I can predict what the voltage on the 1K is going to be, because anything, you know, when we're doing analysis with 1K ohm resistors, whatever the current is, it's typically milliamps. If it's milliamps, the kilo and the milli will cancel. So I expect 2.2 volts here. So 2.2 milliamps times 1K, 2.2 volts. The voltage of the 5.6K, how about that? That's the one over here. Not very much, right? Because there's only 136 microamps of current. Not very much current at all. So we have 136 microamps. Again, V equals I times R. So that's 5.6K. On this one, I'm going to have to do the calculation on. So 136 E negative 6 times 5.6 E3. And I get 762 millivolts. Okay, so very, very, very small voltage over there. How about this 500? The voltage of the 500. Well, I know that the current through the 500 is 2.51 milliamps times 500 ohms. So 2.51 E negative 3 times 500 ohms, I get 1.26 volts. Okay. How about the 2.2K? All right, so the 2.2K has 2.51 milliamps through it, and it is 2.2 kilo ohms. So that's a 5.52 volt drop. Okay, so 5.5 volts here, 1.3 volts here, and then so this one is the, so let's see, 4.7, did we do that one yet? No, we didn't. How about that one? Always does this the worst time. Okay, so the voltage of the 4.7K. So that one has 306 microamps through it. So 306 microamps, 4.7 kilo ohms. Got to get a tray for up here. 306 E negative 6 times 4.7 E3. And I get 1.44 volts. Okay. Now, in terms of what happens here, I'm going to go ahead and erase these. Okay. Now, I just erased that, but Whatever this voltage drop was here, this 5.6K, that's exactly what we should get here because this branch is in parallel with this branch. So that, what the rule for parallel circuits is anything is in parallel drops the same voltage. You can have multiple resistors on that branch, but this total branch here in parallel with this total branch, both of those will drop the same voltage. So I'm going to redo this calculation. So the voltage on the 5.6K was 136 microamps times 5.6K. This one, I'm going to do the voltage of the 1.2K plus 3.3K. And so this one is going to be 170 micro times, if I add those two together, I get 4.5. Okay, so those two voltage drops should be identical. The total resistance on both, and then the current for each branch. So the first one, again, 136E. I guess I got it up here, don't I? That one was 762 millivolts, right? So I expect the same thing here. So 170, whoops, clear, 170 E negative 6 times 4.5 E3, and I get 765. Okay, so essentially the same thing there. Okay, I mean, we're talking about 3 microvolts difference. So that is perfectly acceptable. Okay, now the question, we have to take it one step further, because now if I want to know what's the individual 1.2K, all right? Now I have a voltage drop from here to here with 2 series resistors between those 2 points. That total voltage drop is 765 millivolts. If I want to know individually what happens, I got to go back to my voltage division. So in this one problem, we have utilized Ohm's law, we've utilized KCL, KVL, how parallel works, how series works, and now we're going all the way back to voltage division, okay? So for this one, there is 765 millivolts available from here to here, okay? The total resistance of the two is 4.5K, and so now the individual of 1.2K to that, and then the 3.3, 765 milli times, let's see, it'll be 3.3K over 4.5K. That's really bad, you can't see it, so let me rewrite it. So 3.3K over 4.5K. All right, let's see what this is. 765 times 1.2 divided by 4.5. That one is 204 millivolts. And I expect this one to be bigger because it's a bigger value resistor. Since they're in series, the bigger value resistor gets more voltage. And so that one is 3.3, right? 561. Add those together, you get 765. Okay? All right. Let's see if Multisim concurs. Okay, let's go ahead and see what Multisim has to say. So I did tell you that I would show you how you can use Multisim. I'm going to get rid of the source to find the total resistance, and I'm going to do that now. I'm going to hook up just a regular DMM, maybe with not a little curve there. How about just a straight shot in, and over here as well. Okay, now I want to go ahead and put this into ohm meter mode, and just hit play. There we go, 3.58 kilo ohms, and I don't have it written up anymore, but I believe that is the total resistance. Okay, so that's a good sign. So let's go ahead and get rid of that. So delete, go back and put a source in. Should have controlled X'd it so I can get back to it quickly. All right, so now I've got my source back in. All right. So the first thing I want to do is I want to find what the total current is, and I'm going to go put a probe in here and run it. 2.52. Now I calculated 2.51 milliamps, and so I think that's pretty good. Let's go check my next one, which was this branch. 2.21. That matches up. Let's go check the next branch up here. Okay, so there's the 307. I said 306. Okay, so we're good so far. And down here we should have the total. If we go ahead and put that in, right-click, reverse probe direction, so it's positive. Those two are the same, which we expected. All right, now let's go check these two branches over here. 137 for that one. 170 for that one. Okay, so everything is looking good. So if you've matched all of those up, then you've got all of your voltage measurements proper as well, or you can kind of assume. If I come in here and measure this one, right, 766 millivolts across that resistor, and I could just go put a voltage node probe right here. Okay, so there's 2.2. Whoops, got too much stuff going on here. Back up. This is why. Oh, okay, there we go. Now, resimulate. All right. That probe can go, that probe can go. All right, so if I bring a node probe up here, let's see here. Well, I guess we really didn't find those node voltages, did we? All right. So I think everything has been confirmed here. Now let's try one more. Okay, and the final one that I'm going to do for this chapter, or at least the first part of this chapter. Obviously, we'll have other parts later. But I now have a little bit different. I don't even have a series resistor up here with my source. Okay, so I'm just trying to throw some different scenarios here. Again, I'm going to start farthest away because I want to find my RT. So I'm going to start farthest away from the source, and I notice that I've got this branch in parallel with this branch. Okay, so those are the only two that I'm going to be looking at right now. Okay. So I have to take 1.8 plus 5.6, and I have to take 2.2 plus 4.7. Okay, I know the 2.2 plus 4.7 is 6.9 K. And the other one is 7.4K. So I've got 7.4K in parallel with 6.9K. Divided by plus 1 divided by the other one. Take the whole thing to the -1, and then I'm going to do it this way too, just to double check myself. 1 divided by 7.4. Whoops. 1 divided by 7.4 plus 1 divided by 6.9. And I got the same thing. So 3.57 K. REQ, 3.57 kiloohms. All right, now I'm going to go ahead and redraw the circuit. And again, this is where my green goes. Just pointing out that we're reducing those two all the way down to this one single, that's a resistor, of 3.57 kiloohms. And nothing down here. So this is 1. I didn't give this a value, did I? How about 2K? All right, so there's 1K, 2K. This one is 1.2K. This one is 3.3K, and this one is 700. All right, So now, if I look at the next set, if I do this in orange, hopefully you can see it somewhat. Kind of looks red now that I've painted it with black a little bit. Okay, I've got this branch over here now in parallel with this one. And so these are the only two that I'm considering right now. So my calculation here is going to be this whole thing, which is 1K plus 2K plus 3.57K, which is what? 6.57 kilo ohms. So 6.57K in parallel with, over here I've got 1.2 plus 3.3. I'm not going to write it up there. We've already done one. This one is 4.5. So I'm taking 6.57K in parallel with 4.5K. .67 REQ 2.67K. All right. So now I'm going to replace that and redraw it again. And that one turned out, what did we say it was? We said it was 2.67. Okay. And again, this is where it comes from. We take all of that and replace it with a single resistor. Okay, so now I am at equivalent series circuit. Okay, so now I can say RT is 2.67 plus 700. So 2.67K plus 700 ohms is going to be, what, 3.37 kilo ohms. So my total resistance, 3.37K. All right, I'm going to get rid of this part down here. And I'm going to calculate the total current, because now I know the total resistance. And so now in this problem I have 20 volts divided by 3.37K. 5.93 milliamps. So we know our total current, and that's coming out of the source. And so that is 5.93 milliamps. Now there's no resistor up here, but that's okay. So we also know what the current is through here too. This one is also 5.93 milliamps. Okay. All right. Now that we have that, we're going to go back to, now just work our way back. So we compress it down to a single resistance and then we work our way back step by step. So now this time I've got 5.93 milliamps coming into this node, and it splits here and splits here. The total resistance of those two branches we found is 2.67K. So I'm going to do current division. So the current for this branch, which is 1.2K plus 3.3K. So there's 5.93 coming into the node. And then we've got the total of 2.67K over this branch right here, which adds up to 4.5K. So 5.93 milliamps times 2.67K divided by 4.5K, and we've got 3.52 milliamps. Okay. Now, let's see, 6 and 4. Okay, so that's, that sounds reasonable. That sounds reasonable. Okay, now the current through this other side, which is the 1K plus the 2K plus the 3.57K. So 5.93 comes into the node. 2.67K over, now this one is 6.57. So 6.57. And now I get 2.41 milliamps. So let's go ahead and write these up here. So this branch right here, that one is the 1.2, so that is the 3.52. So this is 3.52 milliamps. I can transfer that up here. because it's standalone. It doesn't have anything else going on out here. So I can transfer this 3.52 milliamps. I wish I had a nicer edge on this one. So that's kind of messy. 3.52 milliamps. Okay. Now, as far as what comes over here, all right, it still goes through this, right? So the other current, this 2.41 milliamps, right? It goes out here, and then now remember, this one out here is these two. So these are going to get that 3.52 as well. Now that's the total current that comes into this node and then breaks up, okay? So the 3.52, I'm sorry, that's not 3.52, that's the 2.41. 2.41. No, that one is the 3.52. This is the other one, sorry. The 1K, the 2K, 2.41. 3.52, okay. So now 2.41 comes into this node, and so now we're going to erase this part. Okay. And really we want to know what's happening up here, so I can go ahead and erase this as well. Okay, but I want to keep those calculations up there. All right, now I want to know the current through this 2.2K plus 4.7K. So that branch, and the total between those two was 3.57. So coming into the node is 2.41 milliamps times the total of 3.57K over the individual branch of 6.9. Found that up here. So let's go ahead and calculate that. 2.41 times 3.57 divided by 6.9. I get 1.25 milliamps. Okay. Now for the other branch, that's the 1.8 and the 5K. And that one added up to what? 7.4. Okay, so 2.41 milliamps times 3.57K over 7.4K. So 1.16 milliamps. Okay, and that sounds reasonable to me. So I'm going to go ahead and say, so through here, the 2.2, we had 1.25 milliamps. And over here, we had 1.16 milliamps. So there we go. We have all of the currents. Again, we could just use the current times the resistance value to find the voltage. But let's go ahead and check in with Multisim and see how we did. Okay, let's go ahead and check in with Multisim here. I'm going to go ahead and throw in a total current measurement here and see what we get. So we get 5.93 milliamps, which is what we calculated. So that's a good sign. Let's go down here and again, right click, reverse probe. 5.93 milliamps, very good. Now let's go check this one, 3.52, and that matches with what we got. Let's go ahead and check up here. Oh, I want to reverse that probe. 2.41, that is what we got as well. So we're on a roll here. How about this branch over here, 1.16? That's what we got. And 1.25 is what we got for the other one. All right. So that essentially concludes this session for Chapter 7. There will be a second part to this where we look at specialized versions of the series parallel circuit. And that will be posted very, very shortly.